Hi students, today I am going to demonstrate another experiment, namely LCR series resonance. Generally we are looking at resonance fundamentals. In this we will do two experiments, namely LCR series resonance and LCR parallel resonance. We will take an inductor of inductance L, a capacitor of capacitance C, and a resistance of resistance R, and these three will be connected in series to a alternating source, AC source, whose frequency can be changed from or between certain range. And for this we use a signal generator or a function generator which is able to generate frequencies of various values. If you take L, C and R and connect them in parallel, then we call it as LCR parallel resonant circuit. These resonant circuits are widely used in various applications. If I take LCR series resonance circuit, that can be used for tuning the various frequencies. This is a tuning circuit. While you are tuning a radio station or a TV station or an FM station, you generally use tuning, and that tuning circuits are LCR tuning circuits. And LCR resonance circuit, first we will do it, and in LCR series resonance, at a resonance the current is maximum and resistance is minimum. You know that when an AC is applied to a circuit consisting of various components like inductance, capacitance and resistance, the net resistance offered is different from the individual resistances offered by the components. The resistance offered by a resistor, a pure resistor, R, is generally called as resistance, and it is temperature dependent but independent of frequency. Whatever the input frequency you are giving, the resistance of the resistor remains the same. If the resistor is of 100 kilo ohms or say 1 kilo ohm, then its resistance will be the same at any frequency. But however, in case of inductors and capacitors, they offer the reactance instead of resistance. Their reactance is a function of frequency. Therefore, loosely you can define that a reactance is frequency dependent resistance. The reactance offered by inductor L is called inductive reactance, and it is represented by XL. The reactance offered by a capacitor is called capacitive reactance, and it is represented by XC. And at resonance in series circuit, the total resistance offered is minimum and it is equal to R, because in series LCR resonance at a resonant frequency FR, XL is equal to XC. XL is the inductive reactance and XC is capacitive reactance. Since both of them are equal at the resonant frequency, in series circuit the resistance offered by the circuit is low and hence the current is more. Yeah, dear students, now look at the apparatus. This is the AC generator, or we also call it as signal generator. And the signal generator, if you see this here, okay, it has multi functions. That's why, and also digital. This is called digital signal generator or digital function generator, which is capable of generating sine waves. If you just switch on this, and if you keep in this mode, it generates sawtooth wave, and if you keep this in this, it can generate a square wave, and whose frequencies can be changed by this knob. You can keep the frequencies either the value shown multiplied by 2 or multiplied by 20 hertz or multiplied by 200 or multiplied by 2000 or multiplied by 20,000. Therefore, here I'll get the value in hertz or kilohertz depending on the multiplication factor. And by changing this knob, you can set any desired frequency. Okay. And if the frequency range of given given range is over, you can switch to next ranges. So I am just powering it. Okay. Now come here now. The signal width height, that is the input voltage of the signal, can be varied by using this. It can be either be kept in 0 to 0.1 volt, or you can keep 1 to 10 volts. I am keeping in the range of 1 to 10 volts, and you can turn this and you can select any value of the input value. And output of this can be taken by using a coaxial cable, or you can use two ordinary wires to take the output, and that can be given to the LCR circuit. And come to here, this is the LCR circuit where the board is having a milliammeter to measure the current in the circuit by varying the frequency. We vary the frequency from the signal generator, and at different frequencies for a fixed LCR combination, we will find out the current in the circuit by varying the input frequency. So we are doing an experiment here to study the variation of current in the given LCR circuit by varying input frequency. Now, if you come here, this is the inductor. If you add these two, then it includes 2.5 millihenries inductance. If you use this common and this terminal, you are able to add 5 millihenries inductor. If you use this and this, you will get 7.5 millihenries. In this experiment, for one set of readings, we will take a common terminal and L2, which includes 5 millihenries. That means in our experiment, L is 5 millihenries. Come to the bottom part of it, we have here various capacitors, and I will use for this experiment 0.1 microfarad capacitor C1. And this is C2, C3 you can use for taking different sets of readings. So L we have taken as 5 millihenries and C we have taken as 0.1 microfarads, and resistance is also you have a choice, but here I'll take the resistance as 100 ohms, and I'll connect all of them in the series for the first experiment as LCR series resonance. So I'm switching on this function generator. You see that the frequency knob, if I'm changing it, the frequency is changing. As it is digital, you wait for some time for stabilization of the value, then note down the values. But if I'm changing, you can change the frequency. Here if you come, here it is now multiplied by 2 hertz. If I take it at 20, then multiply by 20. In this range also I can change it. Now if I keep it in 200 into this. But now for our experiment, I am keeping in 2K. So whatever the value it is showing, if you multiply it by 2, you will get in kilohertz, which can be changed from the lowest value that is showing as 1.17 into 2 kilohertz to, I can go on increasing to higher value up to 10. But depending on the current values, I adjust these values and note down the readings. And here also if you come, you can see that I have selected the sine wave. For resonance, the input is a sine wave. Okay, for this experiment. If you press it again, it goes to sawtooth wave. If I press again, it goes to a square wave. If I press again, it comes to first. So these are the toggling switches. You can go to the required and desired input, sine input. And here I can change the input value. Okay. So I will start connecting the circuit by using the circuit diagram for LCR series circuit. This is the LCR series circuit. We start from the signal generator. One of this has gone to the one terminal of L, and second terminal of L is connected to capacitor, and capacitor second terminal is connected to resistance, and resistance second terminal is connected to ammeter or milliammeter in this case, and the milliammeter is connected back to the signal generator. Therefore, I am now taking the connecting wires. I will connect and start from the signal generator, one of the terminal I have chosen it. And this should be connected to the common terminal. This is the common terminal. And the second terminal is L 5 millihenries. So these are connected in series, and the inductor should be connected in series to the capacitor, and I'll go and connect this to capacitor one end, and this is the second end of the capacitor should be connected to resistance. I take and connect 100 ohms resistance. The other end of the resistance to be taken and should be connected to milliammeter. So I am connecting to milliammeter like this. And the remaining end of the milliammeter should be connected back to the signal generator. Therefore, I am connecting back to the signal generator. And I will now look at here 2K, and I will increase the input, okay, and also I keep this minimum. This minimum is 2K. Now I have connected all the circuits. Okay, so one of the wire is not functioning, therefore I am replacing the wire with another wire, and you can see it, and there is a current because we have already switched on. There is a current, but see that the current, by adjusting the input knob on the digital signal, this you can change the current. So you can change the current, okay. So this value can be changed. So I am keeping somewhere here. We connected LCR series circuit. Before taking the readings, I know that at a frequency called as resonant frequency, we know that at resonant frequency XL, that is inductive reactance, okay, XL is equal to XC, and these are called reactances, but Z is called impedance. The total resistance or reactance offered by the circuit is called impedance Z. And in case of LCR circuit, at a resonance, or say at a FR resonant frequency, XL is equal to XC. But you know that the inductive reactance can be written as, okay, omega F, or okay, omega L, which is equal to the 1 by the omega C. Xc is 1 by omega C. Omega is 2 pi FL is equal to 1 by 2 pi FC. Okay. So by using these two, I can calculate the value of F, or F square, if I take it, is equal to 2 into underscore, okay, if I do more S, F is equal to 1 by 2 pi root LC. Now this is the resonant frequency. So this you can decide it by choosing L and C values. Theoretically you can calculate this frequency. Here in this case, L we have taken 5 millihenries, which is equal to 5 into 10 to the power minus 3 henries. We have taken C as 0.1 microfarad, which I will write it as 0.1 into 10 to the power minus 6 farads. If you know these values, you can calculate the resonant frequency. Now after calculating the resonant frequency, we have to verify practically the resonant frequency. To do that, we have already known that if you draw a graph by varying frequency f here, and if I take current I in milliamperes, okay, then at the resonance, as I'm changing the frequency, with increasing frequency, the value of current increases slowly, gradually, and at certain frequency it becomes maximum. And if you still increase the frequency after this maximum current, this slowly comes and falls down. So it comes and falls down like this. And find out the maximum value from this, and this will be the resonant frequency FR. And this should be approximately equal to the value which we have calculated from the theoretical values of L and C. And from this you can calculate several other parameters also. If I calculate this as I maximum, if I take I maximum by root 2, it somewhere cuts here. And drop the perpendiculars here, and these are called lower cutoff frequency and upper cutoff frequency F1, F2. And find out delta F, which is called bandwidth. It is F2 minus F1. By calculating all this, you have to find out the resonant frequency as a result, and also you need to find out the bandwidth. And from bandwidth, you can calculate a quality factor called as a Q factor, resonant frequency by the bandwidth. Or you can also calculate by the values resonant frequency by into L by R. Okay. So in this experiment, you have to see that now when you are changing the frequency, current should increase and becomes maximum at a particular frequency called resonant frequency, and then it falls down. So thereby, before taking the readings, you can check whether our circuit is working properly or not by changing the frequency and observing the milliammeter. At low frequencies, okay, if you see it, I have kept it low frequencies, the current is somewhere here. So we will now find it out how the current in the meter is changing. Yes, so by changing this, I will see whether my pattern of increase in current with increasing frequency am I getting or not. So I am now increasing this one slowly. Okay, if I am increasing the frequency, suppose say this is the frequency I am keeping here. Okay, so I am now increasing the frequency slowly, and I look at the value of the current. So if you see the meter, slowly I am increasing the frequency, current is also increasing. So at certain frequency, this current should become maximum. Yes, it has become increasing still. It has become still increased, and it has become maximum. Now see, it is taking a return path. That means the current is decreasing. So therefore, we know that from this observation, our circuit is correct and the current is going to maximum and then becomes minimum. Therefore, we will take certain readings starting from lower value of the frequency and the corresponding current values, and the tabular form will be something like this. Okay. I will write the tabular form here. You can see it as, okay, we are changing the frequency, and noting down the values of current. Therefore, first of this is frequency in kilohertz or hertz, you can take it, and then the current value I take it as I in milliamperes. This is the current value. I will change the frequency, note down the values. But for practical and theoretical checking, what I do here is I note down what is the L value. Here I am taking 5 millihenries, and I note down C value. I am taking 0.1 microfarad, and R I am taking it as 100 ohms for this set of readings. Then I note down various values of the frequency. I am now initially start with, see here, it is in 2 kilohertz. Okay, it is in 2 kilohertz range, and then 2 into 1.6 you have to take. Okay, or 1.2, so it is 2.4 kilohertz. For 2.4 kilohertz, like it is 2.4 kilohertz, I have a current of 3 point nearly around, okay, 3 3 milliamperes. So I note down 3 milliamperes. Now I change this value, maybe increasing. Okay, so I change the frequency. I am keeping the frequency around, suppose say 2, means 4 kilohertz, roughly around 4 kilohertz. Then I note down the current. Current is at slightly less than 6, maybe 5.8 I can take it. And I now change this as, okay, it is 2 means 4 kilohertz I have taken, the current value is 5.8 milliamperes. Now I change this value to, okay, 2.5 or so, 2.5 I am increasing, and I note down the value of the current. Okay, roughly around 2.5 I have adjusted. I note down the current as 7. So 2.5 means 5 is the kilohertz, because 2 have to multiply it, and I am getting 7 as the milliamp. Likewise, I am now changing the value of the 1, and see this, I am going to 3, and look at the value of current. Current has increased up to 8. Then I still increase the value, still it is increasing, you see it. So now it is the value of the frequency is 3.31 or 32 into 2 kilohertz. Then I note down the current value here. If I still increase, current is still increasing. Okay, I still increase it, now it is decreasing. So therefore the maximum I am getting somewhere here. Okay, this is the maximum value I am getting. Yeah, this is the maximum value at 3.95. That means around 4, suppose say 8 kilohertz. And then if I am increasing, still the frequency I am increasing, suppose say, still I am increasing it. But look at the meter, it is coming back and coming back. So you take different values until you get the increase in current with frequency to maximum, and then for maximum to minimum, if you take a set of readings, maybe 6 readings while going up to the maximum, and again 6 more readings while coming down, then you can draw a graph, and from the graph maximum value you can find the resonant value. Okay. This type of curve you will get. From this curve you have to calculate the values of resonant frequency, bandwidth and Q factor for LCR series resonance. Now we will go to LCR parallel resonance, and this is the circuit diagram. If you look, L and C are parallel, the two ends of L and C are connected here, and it is connected to the signal generator. Other two ends of L and C are connected, and it is connected to the resistance, and then through an ammeter it has came back to the signal generator. Therefore, here is our circuit. I am now starting the L and C. So I take now common terminal of this, and as per the circuit diagram, okay, L and C should be connected. I am taking the second C because we have already used the first. You can use that also, but I am taking this as 0.22 microfarads. These two are connected. Then this end of the capacitor and other end of the inductor should be connected. That is, other end is here. That means we have included 5 millihenries inductance and 0.22 microfarads capacitance, and they are now parallel here. And from the circuit diagram where L and C are connected, this is L and C are connected. From this, one of the terminals should go to the signal generator. So I am connecting here. You can see here I am connecting. There is a no, and connect this to the signal generator. And from other end where L and C are connected, this is L and C are connected. If you see this, okay, these two are connected. From any one of these two, I am taking here, connecting here. Either you can take or you can take, because both are at the same ends, they are connected. And this should go to resistance. I am taking this resistance. And the other terminal of the resistance, if you take, should go to ammeter. I am connecting to ammeter. And the remaining terminal of the ammeter should be connected back to the signal generator. The circuit is now different. In parallel series circuit, the current is minimum and the resistance is maximum. So therefore, if I keep this as initially minimum frequency, as frequency changes, the current in the circuit varies something like this. I just draw the graph and you see here that, okay, for a parallel circuit, if I take a parallel circuit, I just take this and suppose say this is the frequency I am taking. Either this is the frequency I am taking and this is the current I am taking I. In the case of series, current is maximum at resonance, but in parallel, current is minimum at resonance. Initially, current is higher and it falls down and becomes minimum, then it goes somewhere here. And this is the minimum value of current, you can drop it here. And this will be the resonant frequency FR. So if you can also calculate theoretically the value of resonant frequency, and the formula is slightly different, but you can use the similar formula to calculate theoretical value for this. Now I have shown you how to connect the circuit. L and C are initially connected parallel. From that parallel point, we have added the meter like this. Now, if the frequency is low, current must be higher. I have not changed the range. Range is again 2K and it is showing 1.34 or 35, and that multiplied by 2K is the frequency value. From there, you have to see the current. Current, it is showing higher value. Initially, the LCR circuit shows at low frequencies higher current. Then, if I change this knob and increase the frequency, current will decrease. See here, I am showing here the current will be decreasing. I am increasing the frequency, frequency is increasing, current is decreasing. Okay. So it has come to minimum value, then it is increasing. So it has shown you a reverse trend compared to a series resonance. Initially, when the frequency is low, the current is high. When I am increasing the frequency, current is decreasing, and further it is decreasing and is become minimum. Then even though still I am increasing the frequency, it has to be maximum. Therefore, the current starts at higher value, becomes minimum at the resonant frequency, and again it increases to maximum. So you have to take again 6 readings minimum from the starting initial value to increase and becoming minimum, and from minimum to maximum another 6, you will get a graph, and from the graph you can do calculations.